So quantitative analysis is probably my favorite part of Module 6. I love a good titration question. I think they are really easy marks to get because they're worth so many marks. But if you're good at moles and you are good at kind of workshopping around different weirdly worded questions, these can be really good. So what is titration? There are lots of funny like TikToks about it because it's such a common prac and it's about like turning it pink. There's lots of media on titration because it's so funny. The prac, like when you do the prac, it's actually so fun. The stress of getting the perfect endpoint is something that's really, it's an experience. So have fun doing that prac. But the deepest, corest part of titration is you're trying to find an unknown concentration. And you use neutralization to get there. In this, we assume that the endpoint is the equivalence point. It's not in real life. It's not like that, but we just pretend that the endpoint equals the equivalence point just because it's really hard to get a precise change. And then we use moles and stoichiometry to figure out the concentration of an unknown solution. So moles are really important, molar ratios are really important, and even down to like indicator choice can make all the difference in a titration. But the objective, finding an unknown solution's concentration. What we need to do this is a standard solution. Standard solutions are accurately known concentrations. We know the concentration because we've made it up. We've made it ourselves. It's very easy to standardize, like to figure out the concentration of a substance if we have a good standard solution. And a primary standard is what we do when we make a standard solution. It's when you have to actually dissolve a substance by measuring the mass and all that stuff. The criteria for a good standard solution, a good primary standard solution, is it has to be stable and pure, and it can't absorb water. It has to be hydrophobic, because if it absorbs water, that'll change the mass over time, and that will lead to incorrect calculations of the concentration. And it has to be a reasonably high molar mass. The reason for this is if you have a high molar mass, it prevents small changes in mass, like you're losing a little bit of mass. That won't make a big difference on the number of moles because it's such a high molar mass. It'll be such a tiny fraction of a change. If you have got a really low molar mass, your half a gram being lost on the scale turns into a really big percentage. So you want a high molar mass. And you want an accurately known chemical formula. Sodium hydrogen carbonate is a chill one, very easy to use. I like that one. I don't know how good of a standard it is, but yeah, we used that one time. And how to prepare it, for a primary solution, you need to calculate the amount of solid by finding the mass from the molar mass, and then you want to measure it on a electronic scale. Then you want to dissolve that solid in a small beaker, then change it into a volumetric flask. You want to make sure that you're not losing any of the solution in the beaker. You want to make sure that you're cleaning it out, flushing it out with distilled water so that all of the dissolved bits can get out and you're not leaving anything behind. And then you fill the volumetric flask to the calibration line and then add it until the meniscus is just at the line. It's important that you don't just go filling it up and approximating it at the calibration line. You want to go drop by drop at the end because you want it to be exactly right. Then you insert the stopper and you do inversions. Usually do 5 inversions and then you're good to go. Now, for the actual titration, you'll be very familiar with this procedure by the end of the module just because you're going to do it so many times because it's all about accuracy. And when it comes to like reliability, you want to have lots and lots of attempts at it, I guess. So for the procedure, you need to make sure everything is rinsed with the correct liquid. Now, the correct rinsing is a very important part of titration, and they get so upset when you rinse wrong. So to prepare a pipette, you need to rinse with water, and then you need to rinse with the solution that you will be pipetting. You can't just rinse it with water because then it will change the concentration if there are water droplets still stuck. Then you need to rinse the burette, and you rinse it with water and then the solution that's going to fill the burette. Then you rinse the volumetric flask with just distilled water, and then you rinse the conical flask with just distilled water. So pipette and burette have the extra step of rinsing with water and then with whatever's going in there. Everything else, just distilled water. Don't go rinsing your conical flask with acid or your volumetric flask with acid. It's just not going to work out well. If you rinse incorrectly, you might change concentrations. You might have an endpoint happening earlier than expected. It'll screw all your calculations. So do the rinsing correctly. But once you rinse, what you need to do is you need to use the pipette to measure the solution that you want to put in the conical flask. Put it in there, and then you use your indicator of choice. Choosing an indicator depends on what you're titrating. So for like a weak acid, strong base, you want phenolphthalein. Anything that has a changing point around 7, you want bromothymol blue. And anything that has a little change happening in the acidic region, you want methyl orange. Phenolphthalein is the main one that we use. It's the famous one. It's the pretty pink one. Most of the time you're going to be using that. So you put a couple of drops of the indicator into the conical flask, and then you need to fill the burette, the one that's being held by the stand. You fill that burette with titrant, whatever you're titrating. Then you do a rough titration. You just add the second solution from the burette into the conical flask, and you want to make sure that you're swirling the conical flask because especially with phenolphthalein, like it might look like a drop of pink and you're like, oh my goodness, I've hit the end point, but then once you swirl it, it will go back to being clear. So you need to keep going until the entire thing is pink. But yeah, you want to just keep swirling until the indicator changes color. Then once it's changed color, you repeat it all over again until you have 3 readings that are really close with each other, between 0.05 mils of each other. So when you get to the end of your titration, you don't want to be like opening the tap of the burette and letting everything out. You want to go drop by drop, literally drop by drop, and collecting those drops so slowly. So you need really careful hands for it. And then you perform calculations. So for calculations, these are so much more fun than the theory of titration, in my opinion. I love a good titration calculation question. How we do it is it tells you the endpoint is reached at a certain concentration. At a certain volume, and you're given the concentration of the acetic acid. So it says that you have 25 mils of acetic acid. You can use that 25 mils to find the number of moles of acetic acid because you had the standardized concentration. But above all, the first thing that you need to do is write out your equation. So NaOH plus acetic acid makes sodium acetate plus H2O. Then you use C equals N on V, rearrange it so you can find N to find the number of moles of acetic acid. Then the 1-to-1 ratio of sodium hydroxide and acetic acid means that the same number of moles was used up in the neutralization reaction. So we just put that same number of moles over the volume, C equals N on V. And the volume that they gave us for the titration was 19.3. So that's the volume that goes on the bottom. And that gives you the concentration of sodium hydroxide. Same kind of thing here. They analyzed aspirin tablets for quality control. They had 25 ml samples of a 0.1034 solution titrated against sodium hydroxide. Average volume was that. So same thing, it has a 1-to-1 ratio. So we use the concentration of standardized hydrochloric acid. So we go N equals C times V, 0.1034 multiplied by 25 mils. And then we find the number of moles, and that mole is the exact same amount as the number of moles of NaOH because it's a 1-to-1 ratio. So then you just divide by the average volume required for neutralization, which will give you that, and that's your concentration. Yeah. So it's actually quite simple. It comes down to the molar ratios. We're gonna skip that question because we're gonna run out of time. But now we're gonna talk about titration curves. So titration curves, I briefly mentioned them when we talked about pH probes. But when you got a pH probe, you can stick it in, do a neutralization, and it should come up with a curve that looks like this. The curve changes shape depending on whether it's a strong acid or base, or weak acid or base that you're dealing with. The equivalence point is when neutralization has occurred. And that equivalence point changes location based on the reactants. So if we look at the first one, the strong acid, strong base, equivalence point happens at a pH of about 7, which checks out because strong acid, strong base. And then it looks pretty, it ends at a pretty high base, a pretty high pH, and it starts at a pretty low pH. So that's how we know that strong acid, strong base. If we look at our weak acid and weak base, we have this kind of shape where the since it's weak and weak, it still occurs at a pH of 7, but the volume that it occurs at, not the volume, the base pH that it gets to is much lower. The most interesting shape, I think, is the weak acid strong base because it has this buffer period here. So it's not the same smooth kind of shape as these guys where it's gone denting low like that. It's got this buffer period, and that's because it's an acid. It's a weak acid. It exists at equilibrium. That's showing how it exists at equilibrium. And then equivalence point, blah, 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 blah. And yeah, same kind of thing here. Strong acid, weak base. Got a weird thing going on. Same kind of shape as this one, but yeah, it has a lower resulting thing. Yep, cool. Equivalence point changes based on the different things. So the equivalence point for these graphs are a little bit whack. But for strong acid, weak base, you should have an equivalence point that's closer to the acid side. So the equivalence point should be happening lower. And then for strong base, weak acid, the equivalence point should be happening higher up. So it should be happening like 8, 9 pH over 7. So yeah, that's that. Another type of graph that you might see that you have to interpret for titration are your conductivity graphs. So this is the same kind of thing, but for electrical conductivity, and it's based on the ions that are present. So the most prominent looking V, that's for your strong acid, strong base, and that's because you start off with lots of conductance because you've got a strong acid or strong base, it's dissociated completely, lots of free-floating ions. Then as they start to react, it starts to form water, which isn't reacted. It's not it's not conductive. It's not an ion, so that's not being measured. So the number of ions decreases and decreases as more start to come water. Then when you get to the point at the bottom, That's when all of it has reacted, everything has been equal. Now the upwards slope is just adding excess in. So let's say we keep on adding a base to it. There's no more acid to react with. So it's not neutralizing it, or now it's just accumulating more ions, and that's why it goes back up. So that's how you explain strong acid, strong base graphs. For weak acid, weak base, the most interesting part is the plateau at the top. This is specifically for ammonia, because ammonia isn't like an ion that's charged. Once you've added excess ammonia, it's not going to change in conductance, which is why it plateaus. And same kind of idea for the plateau in the strong acid, weak base one. But yeah, I think that's a pretty good overview of conductivity graphs. Now we talk about Ka and pKa. This is a very good opportunity for the worlds to collide between Module 5 and Module 6. So Module 5 was about equilibrium, and you deal with KEQ, KSP, and you can easily mix that kind of theory with Ka, because it's about the degree of dissociation. So if you look at Ka, it's the concentration of hydrogen, concentration of the ion over the concentration of the acid. So it's basically KEQ, but for acid dissociation. And this just tells us the degree of ionization. A high K means that you have a really strong acid, and a low K means that you have a weak acid, like carbonic acid. There. Basically, if you have Ka, you are able to find out the hydrogen concentration of weak acids and then find out their pH. Because unlike strong acids, where you can just say the concentration of the acid is the concentration of the hydronium, you can't do that for weak acids because it doesn't dissociate completely, which is where you use Ka. So that's how you use Ka, yeah. pKa is like what the same formula as pH, but instead of putting hydrogen concentration or hydronium concentration, you put your Ka there. And this again just shows the degree of ionization. So if you have a low pKa, it means it's a strong acid. Low pKa is a strong acid. High pKa is a weak acid. And this just tells us all we need to know about strength. And this is what we use to figure out the concentration of hydrogen ions for those questions about pH for weak acids. So if we have a question like this, the pH of a propanoic acid solution was measured to be 2.7. The dissociation of propanoic acid is represented below. Calculate the Ka. So first thing to do is write a Ka expression, which will be hydronium on the top multiplied by sorry, that was really loud. I dropped something. Multiplied by the CH3, CH2, blah, 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 blah. Those two multiplied together on the top over propanoic acid concentration on the bottom. So 0.3 is what's going to go on the bottom, because that's our concentration of propanoic acid. Then we need to find the concentration of hydronium and the other thing. These two, we need to find this concentration, and that's where we use the pH. So we find hydronium concentration by doing 10 to the negative pH. So 10 to the negative 2.7 will give us this concentration, and it's a 1-to-1 ratio, so they'll be the same. So it'll be the two same things on the top over 0.3 minus that number on the bottom. Why does it minus that number? It's because it's like an ice table. So really you should draw an ice table, because I low-key forgot about that step just then, and it's really easy to forget about that step. So it's a good idea to draw an ice table underneath. Your initial for this would be 0.3, and then the change will be minus x, and that will make it easier. But yeah, that's how you do that. There are different ways to analyze acids and bases. It really depends on the industry, culture, a bunch of things. main way to do it is using digital probes, like pH probes, to give a digital reading. You can also use it to measure conductivity. There are also some automatic titrators, which can make it more accurate and reliable. Acidity or base or alkalinity can be measured in like a bunch of different industries, food industries, water facilities for making drinkable water, weather, and also with the fruit toxicity removal. All that stuff comes together to use our knowledge of acids and bases for something in society. So like ant stings and blue bottle stings with plant saps, or different acids and bases. That's a way to use acids and bases in society. So that's something like in the syllabus, it's not something you have to write about particularly. It's just something that they want you to appreciate. They want you to understand that they're not only talking about acids and bases because they don't know what else to put in the syllabus. They're talking about acids and bases because it is so present in our society. And that makes them, yeah, they just love to talk about relevant stuff. Chill. Okay. So, some final things. Buffers. Buffers are, if you, I'm a biology kid. I loved biology in high school and I still study biology. So buffers are the most interesting thing in chemistry to me because there are so many natural buffers in like ecosystems and also in our body, like the bicarbonate buffer system in our blood. But a buffer is a weak acid and its conjugate base. And this just means that it can resist changes in pH because since it exists at equilibrium with the weak acid and conjugate base, it can act as it can buffer add additions of both hydronium and hydroxide to act as an acid and a base so that the pH remains constant. And this just means that you're able to buffer these changes in pH. It has to be a weak acid or else it doesn't work. If we look at the acetic acid acetate buffer system, which is the one that I did in class, if you have an acid, the hydronium is acting as the acid, right? So it donates that hydrogen to the acetate ion, and that's the conjugate base. So it donates hydrogen to conjugate base, which will mean that you don't get much change in the pH. If you add a base, you add OH, it needs to accept a hydrogen. So the acid, the acetic acid, will donate its proton to the OH to make water. And that will, again, stop a change happening to the pH because it's counteracted it. So that's pretty cool. There's a bunch of natural buffers in living systems like aquatic environments, blood. I love the bicarbonate buffer system in the blood. It's so interesting. I did exercise science this year, exercise physiology. So there was a lot of talk about the bicarbonate buffer system because it's really important in stopping us from going into a state where our blood is too acidic for us to function and then we die, especially when we do stuff like exercise because you've got a lot of carbon dioxide forming then. But they're necessary to keep the correct pH because pH is it's like the environment, like it's like keeping the correct temperature for your body. You need to keep the correct pH for everything in your body to function. That means enzymes, that means different cell structures. Everything needs to work at an optimal pH. So it's a really narrow window that we're working in, which is why we need buffers to make sure that we're never going outside that window where it might be dangerous. And for like the blood buffer system, the window is like 7.35 to 7.45 pH. So we've got tiny room to work with. So it's really important that we have a buffer system there because we want to make sure that we're buffering properly. So yeah, love natural buffers. Yeah, so there's the dihydrogen phosphate and hydrogen phosphate system in the fluids of cells to keep pH constant in the cells. And same kind of idea here with the dihydrogen phosphate. It acts as a proton donor. So whenever a base is added, that donates a proton. And yeah, for the hydrogen phosphate, that acts as the proton acceptor. So whenever an acid is added, it accepts the proton that's donated by the acid. And that's how natural buffer systems work. So, some final practice questions before I go into either overtime or talking too much about my general HSC advice. Chlorous acid, HClO2, has a pKa of 1.96. Nitrous acid has a pKa of 3.39. And then ask what of the following solutions has highest pH. So the lower pKa means that there is lower pKa means that it's a stronger acid, which means that stronger acid, which means that you have a higher degree of association, which means that usually you have a higher pH. So why is it not chlorous acid? Well, this is because of the conjugate acid conjugate base situation. pKa is a weak. pKa of 3.39 indicates a weak acid, which means that it would have a strong conjugate. And that conjugate would be there. Cool. Here is another HSC practice question. It says that you have these two different graphs and then explain the differences in terms of relative strengths and concentrations. So we can see that acid 2 has the buffer region right here, which means that it is weak compared to acid 1. In terms of the concentrations, you need to look then at how much volume was required. So both were monoprotic, which means both were at a 1-to-1 ratio with KOH. Acid 2 took up way more volume in order to reach the equivalence point, which means that it had a lot more molecules to deal with. So acid 2 is more concentrated, and that's what you have to do. So yeah, acid 1 is stronger because there's no buffer region and the equivalence point is at 7. Acid 2, it just took more base to neutralize it, which means it's more concentrated.